Welcome to this problem-solving session. Today, we'll be tackling problem number 2144, titled Minimum Cost of Buying Candies with Discount. This problem falls under the domain of algorithmic problem solving and challenges us to optimize the cost of candy purchases while applying discounts. Let's explore the problem, break it down, and uncover some efficient solutions. In this problem, we are tasked with finding the minimum cost of buying candies when there is a special discount available. You are given an array called cost, where each element represents the price of a specific candy. The shop has a unique offer. For every 3 candies you buy, the price of the cheapest candy among those 3 will be discounted. You can pick candies in any order to take advantage of this discount. Our goal is to calculate the minimum total cost required to buy all the candies. The input for the problem is the cost array, which has between 1 and 100 elements, where each price value is between 1 and 100. The output is a single integer that represents the minimum total cost to purchase all the candies. Let's consider the first example to understand how the discount works. If the input array is cost equals 1, 2, 3, the total cost of buying all 3 candies is 1 plus 2 plus 3 equals 6. Since we are buying 3 candies, the shop applies the discount, which is equal to the price of the cheapest candy in this group. In this case, the cheapest candy costs 1, so the discount is 1. Subtracting the discount from the total, we get 6, 1 equals 5. Therefore, the minimum cost to buy all the candies is 5. Now, let's look at a slightly more complex example with cost equals 6, 5, 7, 9, 2, 2. To minimize the cost, we first sort the array in descending order, which gives 9, 7, 6, 5, 2, 2. Next, we buy the first 3 candies from this sorted array, 9, 7, 6. The cheapest candy in this group is 6, so the discount is 6. The total cost for this group is 9 plus 7 plus 6, 6 equals 16. For the remaining 3 candies, 5, 2, 2, the cheapest candy costs 2, giving a discount of 2. The total cost for this group is 5 plus 2 plus 2, 2 equals 7. Adding these together, the overall minimum cost becomes 16 plus 7 equals 23. In the third example, the input is cost equals 5, 5. Since there are fewer than 3 candies, the shop does not apply any discount. Therefore, the total cost is simply the sum of the 2 candy prices, 5 plus 5 equals 10. This demonstrates that the discount only applies when there are 3 or more candies. Additionally, we must consider key constraints and edge cases. For example, if there's only 1 candy, the total cost is its price. If there are 2 candies, no discount applies. When there are multiple groups of 3, sorting the prices in descending order ensures we maximize the discount. Finally, if all candies have the same price, the discount is consistent for each group of 3. These considerations will help us accurately calculate the minimum cost in all scenarios. To approach this problem, we considered multiple strategies, starting with the brute force method. The intuition here is to evaluate all possible combinations of candy purchases, applying the discount to each group of 3 candies, and calculating the total cost for every permutation. For every group, we would identify the cheapest candy to receive the discount while summing up the other costs. However, this approach quickly becomes computationally expensive, as the number of combinations grows exponentially with the number of candies. Specifically, the time complexity is O(n), which means it's impractical for larger inputs and unsuitable for competitive programming. Instead, we turn to an optimized greedy approach, which builds on the key observation that to minimize the total cost, the discount should be applied to the cheapest candies. By sorting the candy prices in descending order, we ensure that the most expensive candies are paid for first, leaving the cheapest candies eligible for the discount. The process involves iterating through the sorted array in groups of 3, where we pay full price for the 2 most expensive candies in each group and apply the discount to the third candy. This reduces the computation significantly while ensuring the discount is applied optimally. The sorting step takes O(n) log n, and the subsequent iteration is O(n), giving an overall complexity of O(n) log n. This method is both efficient and straightforward, which makes it the ideal choice for solving this problem. The key insight in the optimized approach lies in how sorting the prices in descending order allows us to control which candies receive the discount. By grouping the candies in threes from the sorted list, we ensure that the cheapest candy within each group gets the discount, which is the most cost-effective strategy. This greedy approach guarantees the minimum total cost, as it focuses the discount on the lowest possible prices in each group. Additionally, iterating through the sorted array in groups of three simplifies the implementation while maintaining correctness. When comparing this approach to others, its advantages become clear. Sorting-based methods, while requiring an O and log n step for sorting, are both efficient and easy to understand. In contrast, the brute force approach, with its O and complexity, is not feasible for larger inputs. Alternative greedy methods without sorting would require more complex data structures to dynamically identify groups of three, increasing both implementation complexity and the likelihood of errors. Thus, the sorting-based strategy strikes the right balance between clarity and performance. The chosen strategy, the sorting-based greedy approach, is both efficient and simple to implement. By leveraging sorting, we ensure that the discounts are applied optimally to the cheapest candies in each group of three. This method avoids the pitfalls of more computationally expensive or overly complex alternatives. It operates comfortably within the problem's constraints, making it suitable for competitive programming scenarios. Importantly, it provides a clear and readable solution without introducing unnecessary complexity. These factors, efficiency, readability, and correctness, make this approach the best option for solving the problem effectively. To solve this problem, we need to minimize the total cost of purchasing candies while taking advantage of the discount rule. For every group of three candies, the cheapest candy in that group is free. The first step in our algorithm is to sort the list of candy prices in descending order. This is crucial because arranging the candies from most expensive to least expensive ensures that the cheaper candies are more likely to be included as free items when we apply the discount. For example, if the input prices are 5, 3, 2, 8, 1, sorting them in descending order gives 8, 5, 3, 2, 1. This ordered list allows us to systematically process the candies in a way that minimizes the total cost. Sorting can be done using standard operations like prices.sort, reverse equals true, in Python, which efficiently rearranges the elements in the desired order. Once the list is sorted, the next step is to process the candies in groups of three to apply the discount rule. For every group of three candies, we add the prices of the first two candies, which are the most expensive ones in the group, and skip the price of the third candy since it's free. This ensures that we maximize the overall discount. If the number of candies remaining is less than 3, we simply add their prices directly to the total without skipping any. For example, consider the sorted list 8, 5, 3, 2, 1. In the first group, 8, 5, 3, we add 8 plus 5 and skip 3. In the next group, 2, 1, we add 2 plus 1 since there's no third candy to skip. The running total is updated as we process each group, and this sum gives us the minimum cost of buying all the candies. There are a few key insights that make this algorithm efficient and effective. First, sorting the candies in descending order is critical. By paying for the most expensive candies first, we ensure that the cheaper candies are used to maximize the discount. Second, grouping the candies into chunks of 3 allows us to systematically apply the discount rule across the entire list. This grouping approach is not only logical but also ensures that the algorithm remains simple to implement. Additionally, handling edge cases is important. For instance, if there are fewer than 3 candies, there's no free candy to exclude from the cost. Similarly, if the total number of candies is not a multiple of 3, the leftover candies are added to the total without any discount. The main data structures used are a list to store the sorted candy prices and a single variable to maintain the running total, which keeps the space complexity low. The algorithm's time complexity is driven by 2 main operations. First, sorting the list of candy prices takes O and log n, where n is the number of candies. Second, iterating through the sorted list to calculate the total cost takes O, n, as we visit each candy exactly once. Combining these steps, the overall time complexity of the algorithm is O, n log n. To illustrate this with an example, let's consider an input list of prices 5, 3, 2, 8, 1. After sorting, the prices become 8, 5, 3, 2, 1. We then process the groups. In the first group, 8, 5, 3, we add 8 plus 5 to get a total of 13 and skip 3. In the second group, 2, 1, we add 2 plus 1 to get a final total of 16. Thus, the minimum cost of buying all the candies is 16. This solution begins by sorting the cost list of candies in reverse, descending, order. The reason for sorting in descending order is to ensure that the most expensive candies are considered first when calculating the total cost, leaving the least expensive candies to be counted as free, if applicable. Sorting is an O, n log n, operation, where n is the number of candies. Next, the algorithm iterates through the sorted list using a for loop. For every candy, it checks its index to determine whether it is the third candy in a group of 3, i.e., when the index modulo 3 equals 2. If it is not the third candy, i.e., I% equals 2, its cost is added to the total underscore cost variable. The modulo operation ensures that every third candy is skipped, as per the problem's discount rule. The total cost is accumulated by summing only the candies that are not skipped. This ensures that the problem's requirement of minimizing the total cost is met by appropriately excluding the cost of the cheapest candies in groups of 3. Finally, the function returns the computed total underscore cost. This solution is efficient, with a time complexity dominated by the sorting step, O, n log n, and an additional O, n, iteration over the list, resulting in an overall complexity of O, n log n. The space complexity is O, 1, since no additional data structures are used apart from a few variables. This is the Java implementation for LeetCode problem number 2144, minimum cost of buying candies with discount. The logic mirrors the Python solution, where the candy prices are sorted in descending order, and every third candy is treated as free. Key differences include the use of Java-specific collections like arrays.sort for sorting and explicit type declarations. The iteration is done in reverse, ensuring that the most expensive candies are prioritized, and the total cost is computed accordingly. To solve this problem, we start with the input array of candy costs, 6, 5, 7, 9, 2, 2. The first step is to sort this array in descending order so that the most expensive candies come first. After sorting, the array becomes 9, 7, 6, 5, 2, 2. Next, we initialize a variable total underscore cost to 0, which will keep track of the total cost as we iterate through the array. Now, we begin iterating through the sorted array. For the first candy, at index 0, we add its cost, 9, to total underscore cost, making it 9. For the second candy, at index 1, we add its cost, 7, to total underscore cost, bringing the total to 16. At index 2, we skip the candy with a cost of 6 because the rule states we skip every third candy, or when I% equals 2. At index 3, we add the cost of 5, updating the total to 21. At index 4, we add the cost of 2, reaching a total of 23. Finally, at index 5, we skip the candy with a cost of 2 since it's the third candy in this group. The result is a total minimum cost of 23. In this example, the input candy cost array is 5, 3, 8, 4, 2. As before, we sort the array in descending order, resulting in 8, 5, 4, 3, 2. We then initialize total underscore cost to 0. Starting the iteration, at index 0, we add the cost of 8 to total underscore cost, making it 8. At index 1, we add the cost of 5, bringing the total to 13. At index 2, we skip the candy with a cost of 4 because it is the third candy in this group, as indicated by I% equals 2. At index 3, we add the cost of 3, updating the total to 16. At index 4, we add the cost of 2, resulting in a final total of 18. Thus, the minimum cost for this example is 18. Here, we start with the input array, 3, 3, 3. Sorting the array in descending order doesn't change the order, so it remains 3, 3, 3. We initialize total underscore cost to 0. Beginning the iteration, at index 0, we add the cost of 3 to total underscore cost, making it 3. At index 1, we add the cost of another 3, bringing the total to 6. At index 2, we skip the candy with a cost of 3 because it is the third candy in this group, as indicated by I% equals 2. This gives us a final total cost of 6, which is the minimum cost for this example. To evaluate the time complexity of our solution, we start by analyzing the two main steps, sorting the list and iterating through it. First, sorting the input list in descending order requires a time complexity of n*log n. This is because Python's built-in sort function uses timsort, which operates with this complexity in the worst case. Next, we have the iteration step, where we loop through the list to calculate the total cost. This step involves visiting each element exactly once, contributing a time complexity of n. When we combine these two steps, we get n*log n plus n. Since n*log n grows faster than n as the input size increases, it dominates the overall complexity. Therefore, the time complexity of the algorithm is n*log n. Now let's examine the space complexity of the algorithm. The input list, cost, is passed as an argument to the function, so it does not add to the space complexity. The sorting operation is performed in place using Python's sort method, which means no additional memory proportional to the input size is required, resulting in auxiliary space. Additionally, the algorithm uses a few temporary variables, such as total_cost and I, to store intermediate values during computation. These variables occupy constant space, contributing 1. Since there are no other significant factors affecting space usage, the overall space complexity of the algorithm is 1, making it highly efficient in terms of memory. Let's compare this optimized approach to a brute force solution. A naive approach might involve generating all possible subsets of candies and calculating the cost for each combination while adhering to the discount rule. This would result in an exponential time complexity of 2 to the power of n, which quickly becomes impractical for larger inputs. In contrast, our optimized solution sorts the list in descending order and skips every third candy, ensuring the highest cost candies are included in the total while minimizing expense. This approach has a time complexity of n*log n, which is significantly more efficient. Furthermore, whether the input is already sorted, randomly ordered, or sorted in reverse, the sorting step dominates the runtime. As a result, the best, average, and worst-case time complexities all remain n*log n. The space complexity, meanwhile, consistently stays at 1. Finally, let's solidify our understanding with a mathematical proof for the big O analysis. Sorting a list of size n requires n*log n comparisons, and this dominates the runtime of our algorithm. After sorting, the iteration step involves a linear pass through the input, contributing n. When we combine these complexities, the overall time complexity becomes n*log n plus n. Since n*log n grows faster than n as n increases, the higher order term determines the final complexity, which is n*log n. On the other hand, the algorithm uses only a constant amount of additional memory, making the space complexity 1. This combination of time and space efficiency ensures that the solution is both optimal and well-suited for the problem. When tackling this problem, there are a few common mistakes to watch out for. First, not sorting the candy prices before applying discounts can lead to a suboptimal solution. By sorting the prices in descending order, you ensure that the discount always applies to the cheapest candy in each group of 3, which minimizes the total cost. Without this step, you might end up applying the discount to more expensive candies, losing potential savings. Another mistake is skipping edge cases, particularly when the number of candies isn't a multiple of 3. If you don't handle the leftover candies properly, your solution might overcount or undercount the total cost. Lastly, relying on an inefficient brute force approach for large inputs can significantly slow down your solution. Checking all possible group combinations has a time complexity of n cubed, which is impractical for larger arrays, so it's important to use more efficient methods. Another common error is using incorrect grouping logic. Some solutions group candies from the smallest price to the largest, but this approach applies discounts to cheaper candies, reducing the overall savings. Instead, grouping in descending order ensures the discount is applied where it saves the most money. Misunderstanding the discount rule is also a frequent issue. Remember, the rule specifies that the cheapest candy in a group of 3 is free, not that there's a percentage discount applied to all candies. Misinterpreting this can lead to completely invalid results. From an interview perspective, these details are critical. Being able to explain why certain approaches fail or how edge cases should be handled demonstrates your understanding of the problem. Now, let's focus on some insights and related concepts. This problem highlights a key pattern often seen in greedy algorithms: sorting the data to make optimal decisions. Sorting ensures you can systematically minimize the cost, and this is a common strategy in array-based problems. Efficiency is another important factor. The optimal solution requires n log n time due to sorting, followed by a linear pass through the array to apply the discount. Handling edge cases is essential too, like arrays with fewer than 3 candies, or those with very large price variations. Additionally, interviewers might ask you to explain the trade-offs of your approach. For instance, why sorting is necessary, or whether the solution could be optimized further by avoiding additional data structures. Finally, you might find it helpful to explore related problems, such as queue reconstruction by height, which also uses sorting and grouping, or candy and boats to save people, which involve distribution and optimization techniques. These problems share conceptual similarities and can deepen your understanding of greedy strategies. For alternative approaches, the most common and optimal method is the greedy algorithm combined with sorting. By sorting the array in descending order, you can systematically apply the discount to every third candy, which ensures minimal cost. This approach has a time complexity of n log n due to sorting, with a linear pass afterward. A potential trade-off here is the overhead introduced by sorting, but it's necessary for the greedy strategy to work effectively. Another option is using a priority queue, such as a max heap, to dynamically extract the highest prices in group candies. However, this approach is more complex to implement and generally slower than simple sorting. Lastly, you could use dynamic programming to track the minimum cost for each subset of candies. While DP can solve the problem, it adds unnecessary complexity, as the greedy approach suffices and is more efficient. Understanding these alternatives can help you articulate the rationale for choosing the optimal solution during an interview. Great job! We've successfully solved problem number 2144, minimum cost of buying candies with discount. To recap, we focused on developing an optimal solution by sorting the candy prices and systematically applying the discount. This approach highlighted how sorting in order of operations can significantly improve efficiency. Thanks for joining, and don't forget to like, share, and subscribe for more content. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!